All right. Okay. Welcome to Thursday's versions of Pollys Introduction to Computer Network. We don't have actually new announcements to make as usual. On Thursday, all the things that we want to announce are done yesterday. There's just one thing today, in the afternoon, 3 p.m. The grades for exam 2 will be released. All right, so look into your inbox and maybe also the spam box, mailbox, for the emails releasing your grades. Okay, all right, so let's go on and start the first topic today. We are not quite yet done with IPv6. Okay, so the next video we'll be playing is about, you see that IPv4 address is 32 bits. And IPv6 is now 4 times longer in address. The number of bits for the address space. It's 128 bits. So obviously the formats are not the same, right? But there are still many machines that are using IPv6. For example, the PA server, that's obviously an IPv4 IP address. How do we send messages from IPv4 machines through other IPv4 routers all the way to reach an IPv6 router or IPv6 machine? How? That technique is called tunneling. Okay, so the way we are ensuring that IPv4 machines and IPv6 machines can somehow work together. And so that at least IPv4 machines messages can travel through IPv4 machines. The messages can travel through the IPv6 machines in the middle of the network and reach IPv4 machines on the other end, so that the IPv4 machines can still read the messages from the source. Okay, so obviously IPv4, IPv6, they don't talk to each other all that well. In order to talk to each other, these machines need to at least be able to speak the other language, meaning IPv4 machines need to have IPv6 there, otherwise it does not interoperate with IPv6 machines. Okay. Similarly, IPv6 machines, they need to speak IPv4 in order to work with the IPv4 machines. And this video is actually not quite about IPv4, IPv6. The two machines needs to speak with each other. It's more that IPv4 machines over here, IPv machines over there on the internet, and there might be some IPv6 machine in the middle. Right? IPv4 will understand IPv4 all right, but the thing is that these IPv4 messages, as you travel through the network, running into IPv6 machine. What do we do with it? IPv6 won't be able to recognize v4 address. Therefore, hey, how do you do forwarding? Because in the table, there's no such IPv4 address. Okay. So tunneling here is to try to get away this problem. 2 IPv4 machines on one end or the other end of the internet. If there's a IPv6 network in the middle, as we try to introduce IPv6 into the internet, there'll be some machines being changed to IPv6. So the IPv4 can still talk to each other, and they want to still be able to communicate with each other, even though that some of the routers are changed to IPv6. Okay, so tunneling here is to address that problem. So this topic is a little bit special. Okay, we will be talking about how we move from a IPv4 internet to a IPv6 internet. You see, there's no way we turn down all the routers in the world and upgrade to version 6 simultaneously and turn them back on and hope that they will just work. No way. It's really, really risky. And hey, we are all living in different time zones. What do you mean by having a flat day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah. Some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. how do we allow the mix of IPv4 router to IPv6 routers? And the technique, okay, let me tell you ahead of time, is called tunneling. Okay, establishing tunnels, okay, between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Okay. Once it hits this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. Okay. So this router will also be doing this. Okay. Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. All right. So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc., etc. Now, IPv4 packet here, coming from the border of IPv4 and IPv6 connection, is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space, and eventually reaching the other end, okay, the other border between IPv6 and IPv4, and that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet, and then forward it further on onto the native IPv6 space here. Right? This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4. I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. Let's suppose we have data we want to send from A to F. Okay? Both of them, version 6, they should be able to send data to each other all right. Now the problem is this. Yeah, an IPv6 packet here will travel through the version 6 space. But as soon as it hits the version 4 space, yeah, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. Okay? So what's being done, okay, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends, okay, exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Once that is done, then let's consider, okay, A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. Destination address is going to be the other end of the tunnel. Okay, the other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E. Then the IPv4 network is capable of forwarding this packet over, okay, at least to E. So E is going to receive the packet next, and being the border router, okay, being the other end of the tunnel, E is just going to extract the blue packet out of the red one and forward it down to the rest of the IPv6 space. And this is when F here receives the packet that is supposed to go for F. All right, so in the video, you see that it's IPv6 packets encapsulated into an IPv4 so that it can travel through the IPv4 network. Okay, but you can imagine an IPv4 packet can be also encapsulated into IPv6 and travel through an IPv6 network to the other end. Okay, so tunneling, it's a technique that people often use to kind of bypass, okay, travel through a network that is a little bit unusual. Okay, so pretend to be a packet in that unusual world until you reach the other end, the exit point. Okay, good. There's just one more video that talks about a lighter subject. So the reason that we need to talk about tunneling IPv4, IPv6 is because, well, it's not like, all of a sudden we change the internet such that it's all IPv6. Okay, so it's actually a slow process. Okay, until today, the adoption of IPv6 might be lower than what you have expected. Okay, so here's the video discussing the adoption of IPv6. Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Ouch, pretty low. NIST is a government body there tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 30%, 33% of the US government internet is IPv6. Okay. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Okay. Ouch. But why, right? If you think at the application layer, we have new applications rising. Okay, IG, Facebook, Netflix, other video streamings. Okay, Zoom, YouTube. Okay, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, network layer changes, it seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app? Yeah, why? Why is it so hard? Well, you know what? Let's come back just a little bit. The adoption rate. So I think Leon was saying that in April 2022, okay, so Leon probably found it on the web. Okay, so probably also look it up. I think there's a wiki page talking about IPv6 deployment. And Google statistics per. So Leon, we might be looking at the same thing. But I think wiki page is probably a little bit outdated, but it's very close to 40%. Okay, and this is almost 30 years. Yeah, it's now 20 more years. Okay, and so it's a very slow process. So just so that you guys know. Okay, Vincent had a question. So every time we have a new design network, we should let the new one to be compatible. Yes, that's actually very important. It's called backward compatibility. When we become more and more large, and it will, such as the operating systems. If you use Windows, it gets really bulky for all these incremental versions. Or if you use a smartphone, the OS on the smartphones always get bigger and bigger and consumes more memory and more memory until like a big version change where the OS companies try to clean things up. But usually when such a new version, new generation of OS is pushed out, is rolled out, people hesitate because there could be a lot of times bugs that are not exactly reversible. I would say that Vincent Wu, it's actually just the things, how the things are, because you want to make sure that people who are using the existing systems continue to use it. Okay, and so it's unavoidable that you need to keep the backward compatibility, and therefore you need to maintain simultaneously the older version and the new version, and encourage the people using older version to change. Okay, now let's see how hard that is to encourage people to change. All right, so let's not talk about how you make other people change. Okay, let's talk about first, have you tried to make yourself change? Okay, it's already hard, you will see, to get yourself to change. So Q1 here, encourage, definitely. So Q1 here, ask, have you ever thought about making changes in your life? Okay. Q2, if yes, did you ended up making the change? Was it successful? Okay. Q3, ask, if it's successful, was it easy? If you failed or failed miserably, why? Why do you think that you failed? Okay. I understand this is a quiz that you guys can all relate to, but I would like you to take some time and think about it as well. I don't know if this is a easy quiz or a hard quiz. I think for some of you it's easy, for some of you it's hard. Okay, let's reflect a little bit, and try a quiz that's not that technical. Okay, so you will have 5 minutes to think about it. right. So, yeah, you guys are, speaking from your heart. I love it. So I see here, Agent is saying, yeah, always, I want to make some changes, right? Whenever things are not going well, you thought about changing. However, however, yeah, it's actually hard to make changes. So you say that I want to do this, and in the end, hey, time flies. I don't, since I always believe it's okay to change tomorrow. There's always another tomorrow. Okay. Yeah, so there are always so many things that you need to attend to, right? And so the change, especially personal change, is set to a lower priority. For some reason, I do find the same thing happening to myself. Victor was saying, yes, yeah, so we are constantly seeking to change so that we could do something a little bit better next time. But we don't have that much time to work on the change. Yeah. Was it easy? Yeah, it probably depends on the kind of change you're trying to make. Some might be easy, but some. It sounded like it's easy, but it actually isn't. Okay. But Victor here is providing a strategy. Okay, maybe you change just a little bit at a time. Victor, that is very insightful. That is very insightful. Guys, that's a very good strategy, you see. Keep the changes you want to make in mind. And if you find some time to do it a little. And gradually you might see that you're getting close to making the change. Kevin, yes? Some yes, some no? Okay, very short answer. I kind of like that. Depends. Some processes are hard, but some is required. I see. So, Kevin, I think, yeah, there are sometimes changes that we are required to make. Ouch. Yeah, so in that case, you just try the best you can, right? And if it's not quite working, life goes on. Try to think positively and, hey, serve more. Okay. Yeah, I hope that's not what, no, I think Vincent was trying to study. Yeah, that's why I get a question from him in the middle of the night. Oh, Naiming, never thought about, okay, good. It's not bad now. Good for you, Naiming. You're in a very good state. And Team 4, Wei Shan speaking. Yes, I always want to cut down on my YouTube time. Okay. Not yet. For some days, I'm able to control myself, but usually I'm not. Okay. Yeah, so that's a little bit of self-discipline. There are always things that you thought that you should not be doing all that much, but maybe. Oh, I see something going on the chat room. Let's see. Even switching to type C also hard. Oh, okay, Kevin. Yeah, so Kevin was saying that making changes can be hard. In case you just purchase a laptop, right, in 2000, like for example, 18 or 17, right, and the ports don't quite come with type C. And nowadays, right, a 4K camera, you need to connect it with type C. So, yeah, changing it to type C, very expensive. Anna, also depends on which changes you're talking about, definitely. Yeah, there's a spectrum of change difficulty, so little by little, it might not be a strategy applicable generally. I see what you're saying. Let's see, Wei San, I can always find excuses for myself. Oh, can't stop watching. It's hard, isn't it? Yeah, I don't know. I guess try to find excuses. It's hard. It's hard. Can totally understand. Oh, okay. Big heart here, definitely. Hmm. Hope that you find the strength to say no to yourself. I think that is the hardest thing to do, to say no to oneself. Okay. Oh, okay. Somebody help you, please. Kevin, yes, I thought about go to bed early. Okay, that I think that's a common change that the students want to make. Cut down on the time you hang on the internet, including YouTube or surfing the web, or yeah, browsing for gossips on Dcard, things like that. Yeah, so go to bed early. One of the top changes people want to make, and it's not yet successful. Human beings have some interesting coherent inertia. When the number of homework is aggregating and exams are coming, it's very hard to maintain the work and rest. I can totally understand. Here, again, hopefully a little bit more love will give you a little bit more strength. Oh, actually add the heart to another post. Sorry about that. Okay, let me give you a heart as well. Cayenne, yes. I did think about making changes. Oh, really? Ouch. Okay. Cold shower every morning I woke up. Wow. Yeah, I know this is mental strength training. I read about that, and I think Japanese exercise this. Okay, cold shower in the morning, and I think some Europeans do this as well. Especially people living in cold area, they want to train themselves to sustain colder condition, so that the everyday coldness is more manageable mentally, at least. It's not easy in the beginning. I usually wanted to my bed and sleep. Yeah, I think winter is coming. You will see that waking up is hard. Yeah, and I accidentally added a heart here. Okay, but I think this is very hard. I cannot imagine myself doing it. Yeah. Really? Pretty relaxing after the cold shower? Ow, okay. But do you do that also in winter? Wow, that is super hard. Let's see. Hey, classmates commented on your post. Oh, okay. Your teammate also, okay, talk about what they want to change. Oh, okay. Howard here wants to do workout continuously. Yeah. I guess it's also hard, right? During the pandemic, it's hard to go to the gym and do the usual exercise you do. I seriously hard. Okay. Yeah, I see. When the weather gets cold, it's hard, isn't it? Would it be cold in Taiwan in winter? Guys, advise Anna. Okay. The temperature wise, it's not exactly cold comparing to North Europe. I know that Ukraine can be really cold, depending on where you live. But don't expect that Taiwan is gonna be much warmer because we are very humid. Okay, guys, advise Anna. Okay, you do want to make sure that you have warm clothing. And I think same here. First center, I met lots of challenge since the culture has changed. Oh. Yeah, I need to make a project out of scratch. Yeah. Yeah, I understand, right? In high school or elementary schools, the teachers usually will prepare you, okay, very well for the experiments, for the assignments. After college, things suddenly change. Yeah, and before you know, the grad school is going to be also a sudden change, and society, even after grad school, another sudden change. Guys, try to not keep your expectation too high. Okay, stay low and humble, okay, and ready for unexpected to happen, and keep going. Just keep going. Um, See if you can relax, walk a little bit, or go to the gym, talk to your friends, um, and keep going. Yeah, the coldness plus humidity, you won't like it. You won't like it. Yeah, it's not easy. Yeah. All right, lots of love to all of you. Claudia, representing also Jade. It's hard. Changing the way of thinking, that is the hardest. Okay, so mental health, guys, there will be always a lot of love. At least from Polly, at least from your teammates, Jade. I know you have very good teammates, right? I feel most of the time change is so hard. So happy to see, right? It can be very hard at the beginning, but if you persist, it gets easier over time. I know that when you were growing up, there's probably not many experience like this. And so once you begin to experience really, really hard time, and if you survive, you get stronger. Okay? Oh, sorry. I can see that it's very hard for you guys. Lots of love. Okay? Yeah, so you know what? I wish that we can go through all of you. I can see that you guys are speaking from your heart. Oh, that's very moving. Yeah. So maybe I'll come back to go over all the changes you want to make and your experience trying to make the change. Okay? All right, so hey, Polly also want to make a change. To be more understanding of you guys. I do learn that makes a difference. Okay, so let's come back to the lecture. How about that? You know what? We do have a new topic we need to break open. Okay, that's called the generalized forwarding. Hey, what is to contrast the generalized forwarding? It was the traditional forwarding. And I recall Claudia asked, is it the destination-based forwarding, destination address-based forwarding? It is. Okay, so the traditional one matches only the destination address. And generalized forwarding, guess what? It's not just matching the destination address. It can be more general. You can match also the source address. You can match also, hey, the port number, which is not exactly level 3. It's not in the network layer at all. Okay, so very general type of forwarding. And here's the video. Last section in chapter 4, generalized forwarding and SDN. So in these SDN routers, okay, the way we're doing forwarding is actually different from the traditional one, therefore we call it the generalized forwarding. In traditional routing, if you still recall, in the data plane, when packet arrives, we look at the destination IP address and we try to match destination IP address to the prefix entries in the forwarding table. If we match one, what we essentially do is to forward the packet to the link interface indicated in the entry. So in the traditional forwarding, yeah, what we're doing in terms of matching, very specific, the destination address. What we're doing as an action is simply to forward the packet further. But in SDN routers, in the data plane, the matching and actions are now a lot more general. This is the architecture of the modern routing, or SDN-based routing. Now, the separation of data plane and control plane, this part is actually very similar to the traditional routing. Now, if you recall the overview of chapters 4, you should recognize in SDN, the control plane look very different. And instead of having routing algorithms running on each individual routers, we now run the routing algorithm centrally on one or maybe a couple powerful machines. And these machines could be slightly far away from the routers in the network. Now, what's a bit similar though between SDN routing and the traditional routing is this. After route computation, we generate tables like this. Okay, this is similar to traditional routing, right? In the control plane of the traditional routing algorithm finished computation generates forwarding table, and we install forwarding table to the data plane of the traditional router. Now, in SDN, tables are generated as well from the routing algorithm computation, and we also install these tables to the data plane of the SDN routers. You see, the control plane to data plane connection there between SDN and traditional routing, very similar. The only slight difference is this. In traditional routing, we call these the forwarding tables, but in SDN, we call them the flow tables. Okay, so each router there will be installed with these flow tables to handle packets coming in. And so the flow table, if we zoom in, it looks more like this in SDN. In traditional forwarding, we have what? Prefix, the first column, and the link interface, the second column. The actions being taken is very simple, matching prefix, and then forward to a link interface. So what we're doing is always forwarding in the traditional routing. But in SDN, these actions could be more general, okay? Not just forwarding. So calling it a forwarding table is a bit awkward. So instead, in SDN, we call it the flow table instead. And by flow, okay, SDN is actually referring to each of these entries, each of these rows in the table. Okay. That is also saying if packets coming into this router, okay, where multiple of them matching a particular header combination and therefore take the same action, they belong to the same flow. So each row here is a flow. Okay, so we have a table of many flows in a sense. So what I'm showing here is also an example. Packets could come in with the headers looking like this, the destination being 0100, source IP address being 1101. Okay. Now we need to go ahead and look up the flow table in this router, okay, and then determine it should go out on interface 2, arriving at this router next. Now in order to do that, there needs to be an entry, let's say this one here, okay, matching the destination and source address. So in the header column, okay, of this entry, there should be specification looking like this. D equals 0100, S equal 1101. Therefore, when this packet arrives, look up, we match this entry and therefore take the action here. Now, forwarding to interface 2, the action there should look like this. Okay, so matching this packet to the combination of header fields and take the action. Now, in the meantime, we take the action, this thing here. Okay, for this entry, the counters, both the packet counter and the data byte counter will be added. So packet counter will be added by 1 for one packet. Data counter will be added by the size of the data here in the packet. Okay, so you see, header column here for matching purpose. Last column here for action purpose. And counter here for management purpose. All right, so that's the general idea. All right, so you see that the table there, okay, previously we called forwarding table, it's now a little bit more general, so it's a flow table, okay. And you see that in the modern routing, as software-defined routing, there's a remote controller, and then these flow table, between the remote controller and the flow table, obviously, right, after the route is computed, those entries need to be installed and become part of the flow table. Okay, so that communication between the remote controller and the router, where the flow tables are, needs some sort of communication. And that protocol doing the communication is OpenFlow. Okay, so the next video is to tell you in a little bit more detail with some very simple examples how OpenFlow works. To put in simpler words, we take a combination of these header fields with specific values, and we define that as a pattern, okay, for a flow. So whenever there is a packet coming in, the SDN router is essentially determining which flow the packet belongs to, because that flow entry is going to tell the SDN router how to handle the packet. That is called the generalized forwarding. So step number 1, the most important step. For each incoming packet, take the header. Try to match the various patterns, okay, in the flow table. If there's a matching entry, go to the action column, so that's step 2, and then handle the packet that way. It could be simply to forward the packet to the next router, or drop in the packet, or modify the packet, or send the packet to the remote controller. So that is usually for debugging purpose, by the way. And step 3, increment the counter so that we track number of packets matching to the flow, number of bytes, okay, matching to the flow. Now, priority. Yeah, so this is something that we have not yet talked about, the priority column. Okay, so the flow table should have actually 4 columns instead of 3. Let me explain why we need priority there. Yeah, these patterns, okay, in the flow table. Some of these patterns could be more coarse-grained. Many of the packets might match the pattern. Some might be finer-grained. Okay, few packets will match the pattern. So if we have multiple patterns that are coarse-grained, chances is actually high that they overlap. Okay, therefore, for a packet incoming, that packet could potentially match to multiple patterns, multiple entries, and each entry specifies an action. So, which actions do we take then, right? So priority there, okay, is to specify which pattern carries a higher priority and which one carries less. So we could differentiate or break the tie among all the matching patterns. Which one should be taken priority, therefore we take the action, okay, in the prioritized entry. Okay, so priority there is to disambiguate all the matching entries. Now in traditional forwarding, we don't need to specify a priority. Why? Traditional forwarding there is to do what? Prefix matching. We do have multiple prefixes existing in the forwarding table. So one packet could actually match to multiple prefixes. Then, you know what? In traditional forwarding, we are also doing the longest prefix matching. That actually breaks the tie naturally, because there's only going to be one longest prefix. Okay? Unlike in SDN, we could have multiple patterns, and the patterns are now general, right? It's not always prefix, so you cannot use the lengths to break the tie. So we have a specific priority field there to break the tie. Okay, so the forward table in the router, 4 column, and it defines, okay, how the SDN handles a packet. It defines the match and action rules. To be more concrete, let's look into 3 examples. Now, in all 3 examples, we look at the source address and the destination address header fields. Now, in example number 1, we don't want to match the source address being 1.2. something. Okay, so the asterisk here meant wildcard, meaning arbitrary values for the last 2 octets. Destination address must match 3.4.5 for the first 3 octets, and then it doesn't matter, okay, what the 4th octet is. Now, all packets matching this pattern will be dropped. In second example, source can be anything, but destination address needs to match 3.4. something, and then we forward all those packets to interface 2. Third entry, 10.1.2.3, as long as the source IP address is exactly this, we send the packet back to the remote controller. So 3 examples, you get a rough feeling. Now, let me come back here. I have not yet explained what OpenFlow means. Yeah, this is the data plane abstraction for SDN routers, all right. Okay, what does OpenFlow mean? Okay. OpenFlow, capital O, capital F. It's a very specific term. It is the protocol, okay, defined for communication between the data plane router to the control plane remote controller. Okay, so remote controller installing forwarding table using the OpenFlow protocol. All right, now let's look closer into the flow table. Okay, so this is the detail. Last slide here is not technical at all. It's to talk about the adoption of conversion. Oopsie, glad that I discovered the link to the video was not quite right. So give me a second. Yeah, this is
with the generalized forwarding explained. Now let's go back to this notion, the flow table. This is one of the most important things in SDN's data planning. Recall early slide. Flow table consists of a number of columns, and you now know it should be 4 columns to be exact. There's this column priority, and we just ignore that here as it's not often used in SDN anyway. The stats column is essentially the counter column in the early slide. There are 2 counters we know, one counting bytes and one counting packets. Action column, 4 classes of actions. One can forward a packet to an outgoing interface, one can forward a packet to the remote control. One can drop a packet as an action. One can also change the content of the packet as an action as well. So, all these straightforward. This column here, very complex. It really depends on the header fields you're using and the values you're using. So the entries, the rule column part of the entries can be very diverse. So the rule column here, in the early slide is also called a header column. The reason it's called the header column is we're using the header fields essentially to compose these rules. In the 3 examples we just walked through, we're using the source and the destination address. These are the header fields in the network layer packet header. One can use other fields in the network layer header for the rule. One can also use fields in the transport layer header, such as the source port number, destination port number, to compose the rule. One can also use the link layer header fields to compose the rule. What's even more amusing is this. These are all fields in the packet headers. One can also use fields that's outside of the packet headers. This is called the switch port. What this means is the packets coming into the router through a particular incoming port. So that's what the switch port meant, the incoming port, the incoming interface. So how we forward the packet can also depend on where they come in from. So that's also why in this slide we refrain from calling this column the header column, because we do have a field that's not necessarily a packet header. So we call them rules in general.
All right, so you see that in the previous 3 videos, including this one just now, we are going gradually deeper. Generalized forwarding, and then open flow, and you see that there are certain columns or certain fields, in each of the entry in the flow table. And just this video, you see, more concrete roles, the structure, and what you can use there for the matching rules. There's one more video that's going to show you exactly the rules. And these rules can be set up for different purposes, not just packet forwarding. But before I show you the rules, let's take a break. It's 11:08 now, and we'll resume 11:18. All right, so break. 1118, good. So, oops. All right, so in the last video, you see that the fields that we match can be general in open flows routing table or flow table. The actions can also be general. Okay, so not just match rules, but also the actions. So next video is going to show you a few examples. We could use combinations of these matching rules and combinations of these actions to create entries, not just for the forwarding purpose, but other purposes that we've talked about that's actually running on the internet these days. So now let's check that out.
Let's take a look at how diverse these rules can be, again through a number of examples. First is the destination-based forwarding. And this is essentially the traditional forwarding, where we look at the destination address. So if you have a packet, the header, the destination field says 51.6.0.8. Now we forward that packet to the output port number 6. So you see here, the SDN router can actually emulate the behavior of a traditional router. And the flow table there is actually a very general form of the forwarding table. Okay. The second and the third example are there to serve security purpose, to set up firewall entries. So let's take a look at what they're doing. First one is actually trying to match the destination port number header field. So if the packet's destination port number is 22, we drop the packet. The second one is actually matching the source address header field. If the packet source is 128.119.1.1, then we also drop the packet. So you see, dropping packet definitely, okay, something that the firewall does. Now, why blocking packet going to port 22? Why blocking packet coming from a particular IP address? Allow me to explain. So port 22 is also the port number of the SSH server. So this is the server that you contact to every time you try to log into the workstation. So after you type in SSH, what do you do next? You give the username, right? And then the server is going to prompt you for password. The hackers around the world is trying to SSH into the machines around the world. Using what? A min or a root username and guessing the passwords for the root or a min. Now, if they guess the password right, then they get into the workstation and they get to play around and set things up or change things or encrypt your PA assignments and then send you ransom emails. Okay? So blocking packets to port 22 is to block any logging request to port 22. Therefore, SSH is disabled on the machines behind this firewall. Second entry there. Okay, so this is actually more to try to prevent this attack. DOS attack, denial of service attack. You see, system admins around the world, especially those who are experienced, they will go up to these websites where the system admins share IP addresses of zombie machines. So if one day a hacker hacks through the workstation and take over the workstation, 140.112.42.161 is going to be a zombie IP address. So the experienced system admin, after looking up the website displaying all these zombie IP addresses, can set up these entries with the zombie IPs here. That would actually block all the zombie incoming traffic if a higher level hacker comes in and asks all the zombie machines to issue, for example, login requests. Then our machine is going to under attack. So experienced admin setting up these entries ahead of time will prevent us from the DOS attack. And this attack is also called the SSH brute force attack. Guessing the password by repeatedly trying, that is a brute force attack. Example number 4, destination-based layer 2 forwarding. I know we have not yet talked about the link layer protocols, aka the layer 2 protocols. So this entry here could sound a bit fuzzy to you guys. Now, so let me tell you ahead of time what the purpose of the entry is. So with this entry, the SDN router is emulating the behavior of a layer 2 switch, of a Ethernet switch. I think we've seen something like that when we're talking about the subnet, right? Within a subnet, there are these interfaces that are connected, but the connection is there through a switch, through a link layer switch or an Ethernet switch. So you see, from one machine, this network interface could have a frame passing through and coming to the link layer switch. Now, this link layer switch, we need to look at the destination address, but the link layer destination address to decide how to forward it further so that it reaches other interfaces on the same subnet. Okay, so that is the use of the switch there. So you see why. This entry here is looking at the destination address and the link layer. That is also called the MAC address, and it looks very different from the IP address. So if this packet comes in matching this link layer address, then that's forwarded to output port 3. Right? So that is the idea.
Yeah, so you see that a SDN router, that flow table, can be very powerful to make that SDN router a firewall. A lower level link layer 2 Ethernet switch, and of course working like a traditional router, right, through the destination base forwarding. And quiz 36 is to show you a set of rules. They are used in combination. Okay, so the way you want to understand quiz 36 is this. So there are actually 3 machines. Okay, so there's a laptop at the top. This is where the user is. And that user tries to send traffic through some kind of server and then going to a destination. Okay, the IP address look a little bit familiar, right? So this is the PA machine, PA server. Okay, so this rule, okay, is set in the client machine. Let's assume that all these 3 machines, although it looks like a laptop, looks like a server, looks like a desktop, think of them as SDN routers, okay, running open flow, okay, with some sort of remote controller. And remote controller installed to this machine, this entry. And the remote controller installed to this machine, this entry. What do you think these 2 entries are for? Okay, so that is quiz 36. Okay, you might need to think a little bit, but the answer is very straightforward. You will go, oh wow, yeah, you're right. Okay, so think about it. You have 3 to 5 minutes. Yeah. Okay. So maybe I should elaborate a little bit more. If you look at these two entries, the action field. Okay. So you see the action field is not like a port number or not a drop, certainly. So it's obviously not a firewall rule. It's certainly not a forwarding rule. Okay. In the action column, you see the first rule here says, oh, destination address should be changed to this 140.112.2.110. So look at this. If the packets matching this source IP address, this destination address, this source port number, this destination port number, the packet's IP address destination needs to be changed to this address. And the port number changed to 1194. Okay, that is what? This value here needs to be changed to this. And this value changed to this. And so, the packets coming from the client, coming out of the client, as long as the destination is going to this particular destination, it will be changed to this first, therefore being sent to this machine in the middle. And then as the packet coming into this middle server, hey, it will run into another entry down here. And if we match the IP source and IP destination to this pair, oh, hey, we just changed the packets from 221 to 110, and here we match again. And the actions this time on the middle server is this: change the source address to 140.112.2.110. Destination, okay, back to 221. And so this packet, destination address was here, therefore it arrives at the middle server. But here, it actually changes it back to 221 and send it out. So what is this doing? Yeah. Oh, okay. I see. Vincent is quickly saying VPN. Yeah, it is. Yeah, I think Agent and I think Agent also gets it. It can be a manning the middle attack or manning the middle defense. You know what? VPN is used very, very often for DDoS. So Agent, you're actually right. Both by saying it can be an attacking point or defensive point, and of course acting like a VPN. Good. Yeah, it will eventually reach the server on 221, so Kevin definitely is correct. Yeah, so it's used to forward the request from the client to 221. But the question is, how come, right? Why can't we just send the message out directly? Why the first entry here? So in a way that we're redirecting that message to somewhere else and then to 221. So that is because 221 has a firewall that blocks sources that are coming from outside of 140112. Okay, Vincent, very well done. Okay, with that said, I think you guys all kind of get it. Yeah. So action field here, you see that there are more what people can do. Not just dropping a packet, not just forwarding a packet to a particular port. You can also change different fields in the packet. But here you might thought, oh, this is cool, but how did the client know that it needs to set up the top entry? How did the middle server know that it needs to set up this entry? Yeah, usually there's a remote controller doing all the necessary calculation to figure out how these rules should be like, and then install these entries using OpenFlow to the SDN routers. Okay, so as I mentioned earlier, you pretend all these three machines are SDN routers. And it's in fact not that far off. You can actually install the operating system of these SDN routers on many of the machines that you can easily buy from the Guanghuang market or online. And it will be a SDN router. But usually the higher end SDN routers needs accelerators doing quick rule matching, very quick rule combination matching. Okay, very good. So I think many of you guys get the idea. Okay, those who are still pondering, it's okay, take your time. All right, and let's move a little bit faster. Okay, the rest of the lecture, because we have one more quiz that we're trying to see if we can make it. All right. Until now, what we have talked about are OpenFlow, SDN router, how remote controllers use OpenFlow to install rules. Okay, but this is not quite a full example of a OpenFlow based network. Okay, so next is a video that introduces a full example. Okay, OF OpenFlow.
With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match, okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing packets. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN, okay, is a very general machine that unifies, okay, a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. So you see here, this network, okay, is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the OpenFlow protocol. Right? So this controller here, sometimes being also called the OpenFlow controller. Just like the SDN routers, okay, some of them will actually call them the OpenFlow routers. A scenario is this: let's send packets from H5 and H6, here and here. Okay, from subnet 10.3 to H3 and H4, H3, H4, subnet 10.2, okay, but through a very specific route, okay, from S3 here through S1 and then reaching S2. So we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this. Okay? If you want to send data from 10.3 subnet to 10.3 subnet, because this is only one hop. Okay? This is the shortest path. Traditional routing does not provide you the flexibility of manually configure a specific route. But hey, luckily we have the OpenFlow controller. So OpenFlow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, and S2. And these entries will look like this. Okay? Inside S3, the flow entry will look like this, source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now, the entry in S1, this router at the bottom, will look like this. If the ingress port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 flow entry looking like this. Ingress port being 2. So packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. All right, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So there I got this one. On the other hand, if it's 0.4, then forwarded on interface 4, therefore reaching H4. So OpenFlow, really nice and flexible. So something to add is just here. Traditional routing implements a routing algorithm. You know what? The controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional routing.
All right, so that's exercise. Okay, so quiz 37 is asking Q1, which way would traffic go from host 5 to host 4? So let's see, on the graph, which one is host 5? I think it's up here, upper left, 10.3.2.1. Where is host 4? I think lower right here, right? 10.2.2.1. Now, according to the flow table, on router A, on router B, on router C. So what would the traffic from H5 to H4 flow? All right. So the destination address must be 10.2.2.1. The source, 10.3.2.1. And this packet coming from H5 would run into router A, therefore being checked down, okay, through this flow table. Matching, if the source is 10.3. something, okay, that's matching H5's source IP address. And the destination is 10.2. Hey, is it 10.2 here? Yes. What do? We forward the packet to interface 3. Which is here. So the packet will go downwards, isn't it? All right, now you do the rest, okay? Q1, which way would the traffic go? All right, and Q2, suppose H4 needs to send traffic to H5 through B. Oh, okay, H4 here. The router connecting H4 is C. And we do want the traffic to router C, finally reaching H5, travel this way through B. So we want to enforce, in case the source is 10.2.2.1, destination is 10.3.2.1, that traffic needs to flow this way. So we might need to change table here, as well as table here, or adding entries. Okay, in order to enable traffic going from 4 to 5 through B. So how would you need to change these 3 tables? The table at router C, the table at router B, and table at router A, such that we could do this from H4 to H5, going C, B, A. Okay, so you might need to change entries, you might need to add entries. Okay, so this is gonna take a while. Okay, so why don't we allocate a good 8 to 10 minutes time, okay, so that you can really work on it. All right, so take your time. You have 8 to 10 minutes. Okay, so let's begin. So Polly will actually have to work on it as well. Yeah, so I guess it's a good thing that you're given a longer time. Yeah, so I see that you guys are more comfortable and take your time into thinking, and I see that you guys are all tackling the problem here. Very good. So yeah, that was open flow and a full example. Okay, in an enterprise network or bigger, okay, business-oriented network. Nowadays, there's a higher percentage of these networks managed using SDNs. Okay. Big companies such as Google, Amazon, they were all using SDN. Okay. I don't know about NTU though. I don't know about NTU though. But I do notice that NTU's dormitory network management is quite complex. Um, but I complex in a way that it's not very easy to manage. But I guess it's a good training for students who are interested in computer engineering. Mhm. Good. And you know what? It's time we move on. And move where? A new chapter. Okay. You see that so far we've talked about chapter 4. It's all about the data plane. It's the forwarding plane. Okay. There's still the control plane, the routing plane that we have not yet talked about. So let's start and break open chapter 5.
Chapter 5, Network Layer, the Control Plane. Control plane is also what Polly likes to joke about, the better half of the data plane. Now the reason for that is this. If you think about data plane, that forwarding function there, what it does is simply, right, for each incoming packet, do a table lookup, and you know what to do with the packet. Okay, so for each incoming packet, one table lookup, and that's it. There's nothing really intelligent about it, right? The only thing the forwarding is doing just table lookup, and it's just pattern matching, right? But hey, we're sending all sorts of packets coming from different sources, and they're going to different destinations, right? You cannot be sending these packets to arbitrary directions and hope that they will reach the destination. No. So that table there is really where the intelligence is. That is really, okay, guiding the packets to go to the right direction, eventually reaching the destination. So the data plane, the forwarding function, although very busy, working tirelessly trying to forward packets, okay, but it's actually simple, stupid. Intelligence is right here in the control plane, and the intelligence is implemented using these, the routing algorithms. Okay, so routing here, what I meant as a function is to find a path, okay, for a particular source to be able to send packets to a particular destination, or to find a path so that packets belonging to a flow can flow through the network, okay, with the right amount of resources reserved. Okay, so routing algorithm there, very intelligent. Okay, so in fact, the first part of chapter 5 is going to sound a little bit like you're attending a algorithm course. So Polly will be speaking about two general routing algorithms. Okay, so they are graph algorithms. So provided a graph, okay, if you think about it, a network having machines connected by cables is a graph, right? Points connected by lines. So provided a graph, we could calculate, we could compute the shortest path from one arbitrary point to another point. So that is what the magic of derouting algorithms are. So these two general routing algorithms will be implemented on the internet as two routing protocols, OSPF and BGP. We'll talk about these routing protocols later after we finish describing the general algorithm. Now, these routing protocols are running on the traditional routers, where you have the data plane and the control plane. So the routing algorithm is running in the control plane. Okay? The control plane of each router might be communicating with the control plane of other routers, and together they complete the task of calculating routes, and in turn generating the forwarding table, and in turn install the forwarding table to the data plane, and in turn the forwarding function, okay, can be working really fast. Now, the new model of doing routing is called SDN, software-defined networking. So the one that's doing the route computation is the controller. Okay, this is also known as the what? Remote controller, because in SDN, okay, the model is slightly different. You still have the data plane doing the forwarding, but the control plane is implemented outside of the routers. Okay, in fact, powerful machines somewhere remote. That's why these controllers are also called the remote controllers. Okay. And between the remote controllers routing, okay, is being done where we generate the flow tables. And the CA, the control agent, now in the data plane, okay, that's taking in all these tables being transferred from the controller, okay. In between, there's this open flow protocol, okay. Now you should know after chapter 4. So after the control agent receiving the flow table, the flow table gets installed, and therefore the SDN routers can do flow table lookup, okay, do generalized forwarding. Now, the remote controller here, okay, it's actually quite general. Inside the remote controller, you could implement multiple routing algorithms, such as the one used by traditional routing. You can also implement other routing algorithms, and in addition to all these routing algorithms that could be running simultaneously, and you pick and choose a particular route for a particular pair of source and destination. You could also actually specify preferences, or specify costs, okay, or specify other functions. Okay, so SDN's remote controller, being very general, okay, is actually working like pretty much a regular computer, okay, or expensive servers. So on these SDN remote controller, okay, we run operating systems, elaborated operating systems, such as ODL or ONOS. Okay, so these are two different operating system architectures, and both have big camps of supporters. So SDN routers are made available today that both operating systems can be installed, okay, to support route computation, flexible route generation, flexible flow table generation. Okay. So these protocols, as well as these two, okay, of the technical components in chapter 5, concern the routing function, the second important function in the network layer. In the control plane, okay, we also implement some protocols that is to do this, the management, okay. So management of the routers, or the routes, or the packets traveling certain routes. Okay, so those are called the ICMP. So ICMP there is to allow generation of special messages from the routers or from the host to the routers, and routers generating something back. So these are there for the network admin to sort of probe the network to find out, okay, where and what might be going wrong inside the network. SNMP. Okay, so SNMP there, the management protocol is more there continuously tracking, okay, the statistics of the network. For example, number of packets traversing a router, number of packets traversing a route, okay, number of routes on a router, and things like that. So that the network admin can know better the status of the routers, the status of the routes. Okay, so again, for management purpose.
All right, so that's the overview of chapter 5. As you see that Polly listed the major topics: routing, right, SDN, and then ICMP, and then the management. So SDN will be able to talk a little bit about it so that you get your foot into what SDN routers are like, architecturally speaking. And we'll definitely talk about routing because it's the most important function in the control plane. Okay. But for ICMP and SNMP, we won't have time to talk about them. They are just like the traditional IPv4 ICMP, IPv4 SNMP. Okay. And before we start talking about routing, there are two questions. I think first from Youxiang. What is the purpose of taking a detour in the example? Okay, so that was, I think, maybe I can go back a little bit here. I think that is I think quiz 36, right? The SDN flow entry example. Now we kind of know that this is VPN. So the purpose of taking a detour through 140.112.2.110, that is because there is likely a firewall set up 140.112.42.221 so that 32.227.45.90 won't be able to connect directly, okay, to the end machine. Okay. So originally the laptop wants to connect to the desktop, but there's a firewall entry on the desktop. Okay, and that firewall entry, slide 87. Okay, so let me see. So maybe it's a little bit more like quiz 37. Take a detour. Oh, do you mean that taking a longer route instead of the direct route? I think you probably meant that. Sometimes, yeah, sometimes. Um, it might appear that if you want to send data from A to C, so for example, from host 5 to host 4, isn't A to C the direct path? You know what? That is right. But in a SDN network, because a lot of times you do a lot of monitoring, measuring, if you want to track the traffic, a lot of times they might just pass the data through router B, where B might be a monitor. So B, that router there can be doing some accounting. Okay, and some traffic doesn't need to be monitored, can go on shortest path A to C. So you see that on the internet nowadays, because internet is very business driven, therefore it's not always that the network admin would prefer the traffic going the shortest path. It can be because of policy, it can be because of management purpose. They route or detour traffic so that they can log something, so that later on they can come back and try to debug if there's some trouble, some abusive users, for example. So I can imagine a case, maybe there's an abusive user from H5 and it's frequently probing H4, and it looks very much like a denial of service attack. Then that traffic from H5 might be redirected through B to C, and be there monitoring closely the traffic pattern and see if it matches certain DOS pattern. If it does, then they can write an email to the abuse, so the network manager of network A there. Okay, so it's different. So people can always come up with different reasons that you might want to reroute the traffic somehow, and not always going for the best performance. In this case, delay is going to be longer for sure. Zijun was asking, what is matching ingress port for? Okay, that's a very good point. I mean, you can always, right, use a source IP address, and then you could determine for a traffic coming in from interface 1, and it should go certain direction. But sometimes you might have a special router, okay, that is to do, for example, load balancing. And so if certain traffic coming from interface 1 versus coming from interface 2, they want to just separate them, and they will go off to different interfaces. So think of a load balancer router there, or a load balancing SDN. Then it might be easier, right? Just judging the incoming interface and then direct them out to different interfaces. Yeah, so in a way, Zijun, so it's actually to provide some more flexibility, some other ways of configuring these flow tables. You can always look at the source IP address, but looking at the ingress port number is just another option. Okay. I think what's hard in SDN-based routing is that you don't know, right? If I set up an entry, maybe the next network admin, okay, that's taking the ship over, might set up another entry, and the two entries might conflict each other. One entry says traffic should go that way, and the other entry says traffic should go the other way. Usually, if you set the priority carefully, then you can resolve conflict like this. But you see that after all, these entries are set by people, or people's program, okay, that generate rules. Therefore, there could be conflicts. So some of the guys doing internet research these days are trying to come up with a software-based solution to detect flow table entry conflicts. It's very interesting. Some of them use a graph theory oriented approach and see if there are overlaps. So it's a very, very interesting hot topic for internet research. I think Chandy has a question. Why do we need to indicate ingress port instead of just indicate the source port number? Okay. The ingress port is actually meant, so for example, router B here, this is port 1, this is port 2, and this is port 3, and this is port 4. So when we say we want to match ingress 1, we actually meant all the packets coming into router B through interface 1. Okay, the source port number, that is actually the original traffic source's port number. Okay, so if host 5 is the source and the port number that this source is using to generate and output traffic, that is the source port number. Yeah, so that's actually far off, maybe several hops away, while this one, ingress port, okay, here actually meant the router's interface. There are several of them. If the packet is coming through a particular interface, it's treated specially or it's matched specially. Okay. Yeah. So sometimes you want to do traffic redirection, as I mentioned earlier. Having these ingress port, not exactly the source port, can be helpful. Okay, so I hope that addressed the question. And now let's start talking about routing. And before we start talking about routing, let's review. Okay, routing. Okay, the control plane, data plane again, and what is general routing, SDN routing. Okay.
Let's go real fast through 5.1, the introduction. Again, network layer, we run two major functions, forwarding and routing. Forwarding is about moving packets real fast from one router to another. Routing, however, is for each router to generate this forwarding table or flow table, or to determine the routes for the packets to move, okay, from one to another router. So, in chapter 5, we focus on the control plane here. The two models, okay, for route computation are these: the traditional routing versus the SDN routing. In the traditional routing, each router implements part of these routing algorithms, and so the route computation is somewhat distributed, and the routers work collaboratively to come up with the best routes. Okay. So there's per router control plane doing the route computation. But in SDN, okay, the route computation is more centralized, running on powerful machines, and also somewhat distant from the physical routers. So centrally controlled. And this control is called the remote controller, as they are being physically distant from the router. More specifically, in traditional routing, okay, the routing algorithm is implemented and running on each of these routers, and they'll be interacting with each other to generate the best routes, therefore coming up with the forwarding tables. Okay, so in the data plane, yeah, there's this forwarding table in the data plane. The control plane there runs the routing algorithm, and together they generate the forwarding table and forward it and install it in the data plane. Now, the modern routing, the SDN routing, works this way. Okay? There's going to be a remote controller there, okay, doing all the computation and then interacting with the local control agent to install these forwarding tables, or more precisely, flow tables. So router, yeah, data plane here, having these control agent, and then at the control plane, we have powerful machines running the remote controller. Remote controller interacting with the CA, setting up these flow tables.
For today, because we run out of time, all right? So we'll begin talking about routing and start by the notations, and then we'll talk about the first routing algorithm called the link state routing algorithm. Okay. So those who have taken graph algorithm before, Dijkstra algorithm is the algorithm being used by the link state routing. Okay, so that's just a little bit ahead. With that said also, I see you next week. Okay, bye, guys. PAA might not be that trivial. Definitely don't wait until Friday to start working on it. Okay, try to start as soon as you can. Okay, bye. Okay, bye. Okay, bye.